Hello guys, welcome back to the university, and in this video we're going to talk about half-life. But before anything else guys, please extend your appreciation and give this video a thumbs up. Like this video, share our content, and please subscribe to the university, and don't forget to hit the bell icon so that you will be notified whenever we post new videos like this. Alright, so let's go on and discuss what is half-life. So half-life is defined as the amount of time required by a radioactive substance to reduce to its 50% of the original content. Basically, this has something to do with the decay of the atom or of the nucleus. So as the name implies, radioactivity is an act of emitting radiation spontaneously. So this is done by an atomic nucleus that for some reason is unstable and it wants to give up some energy in order to shift to a more stable configuration. So there are decay process, one of which is what you call the alpha decay, and it is defined as a nuclear decay process where there is an unstable nucleus that changes to another element by shooting out a particle composed of two protons and two neutrons, which is also called a helium nucleus. So this ejected particle is also known as alpha particle and is simply a helium nucleus. So the next other two are beta decay and gamma ray emission. So we define beta decay. So beta decay is a radioactive decay in which a beta ray is emitted from an atomic nucleus with some particles associated with it. So during the beta decay, the proton in the nucleus is transformed into a neutron, or a neutron transformed into a proton. So there is a vice versa. So there is a conversion of neutron to proton, proton to neutron, and vice versa. If a proton is converted to a neutron, it is known as beta plus decay. Similarly, if a neutron is converted to a proton, it is known as beta negative decay. So gamma decay is a type of radioactivity in which some unstable atomic nuclei dissipate excess energy by emission of spontaneous electromagnetic radiation. So in most common form of gamma decay, known as gamma emission, gamma rays like photons or packets of electromagnetic energy of extremely short wavelength is radiated by the atom. Okay, so um, after undergoing this decay process, the nucleus changes and the original material gets reduced. Alright, so radioactive decay is very random and we are unable to predict what nuclei will undergo decay process, but the rate at which it happened is nearly constant. So there is a we are able to predict how much of the sample remains after a certain amount of time. So this means that a certain amount of material will decay only after n years, and that's always nearly constant. Okay, so let's for example assume that we have 100 tomatoes and the half-life of them is 10 days. Okay, so basically if you have 100 tomatoes, only half of it remains after 10 days. So we can tabulate the decay process as seen in the table below. So this is the table guys. So for example, we have 100 tomatoes at the onset of the decay process, so that's the time is 0 days. Alright, so after 10 days, which is one half life, so 50 tomatoes will remain. Alright, so after 20 days, only 25 tomatoes are left. After 30 days, you have 12.5 tomatoes left. After 40 days, you have 6.525 tomatoes left. And after after 50 days, you only have 3 tomatoes. After 60 days, you have 1.5 tomatoes, and after 70 days, you will see that you only have less than 1 tomato left. Alright, so this is the decay process. You will see that as time passes by, every 10 days, the amount is half. Alright, that's why we call it half-life. Alright, so you will see that we can use the table to determine the total number of days before nearly all tomatoes decayed. So how do we do that? So we add all the days that passed by, and we will have, so we're gonna add 0 days, 10 days, 20 days, 30 days to one another, and so on and so forth. So basically, we have to sum them up, and the time passed by for all the tomatoes to nearly be gone is equivalent to 10 plus 20 plus 30 plus 40 plus 50 plus 60 plus 70 is 280 days. So after 280 days, nearly all the tomatoes were decayed. All right. Notice that half of the same of the sample remains after its half-life passed by. So just for example, after 10 days, which is said to be the half-life, only 50 tomatoes were left from the original number of 100, and the pattern continues to progress in that fashion. So we can derive a formula using the table below. Alright, so half-life cycle is tabulated right here. Alright, so we have 0 half cycle, so 0 days have passed by, is no tomatoes were decayed, and after one half-life, which is equivalent to 10 days, 50 tomatoes were uh, left, and after 20 days, all right, two cycles of their half-life, only 25 were left, and so on and so forth. And you will see that there is a ratio 100 100, and here you will see that only half remains after one half-life, and you will see that 1/4 of the original sample is left and after uh, 20 days, and the pattern continues. Pattern goes on and on. All right, so let's use another. So you will see here that so you will see here after, yeah, times 10 days, so after 20 days, yeah, 25 tomatoes were left, and that is 1/4 of the original sample. All right, so after 30 days, all right, 3 times 10, or 3 half life cycles, after 30 days, only 1/8 of that sample remain, which is 12.5, and so on and so forth. All right, so we can express this into its exponential form. All right, so 1 raised to 0 is just equal to 1, and 1 half raised to 1 is 1 half, and 1 half raised to the power of 2 is 1/4, and so on and so forth. Alright, so we will see that by following this table, we can formulate an equation, and yeah, so we can see that by multiplying the original amount to the ratio will give us remaining amount of the sample after time t. Okay, so hence we write the suggested equation as remaining sample is equivalent to the original amount. All right, so this is our relationship. All right, so original amount, yeah, so there we go, times the original ratio. All right, so let's just erase that. Yeah. All right, so this is our proposed formula, and we let S sub r to be the remaining sample, and A sub o as our original amount. All right, so furthermore, we let r to be the rate, okay, at which the decay process is happening, and t will be the time that passed by, and h sub t is the half-life. Okay, so we have, so this one is the remaining sample, and A sub o is our original sample, and we have the rate. So this is our formula. Okay, and next is we see that the rate is just equivalent to the one half, okay, which is constant because every time the sample reduced to one half, and t is the time that has passed by. All right, so let's say for example that's 10 days, and or say for example 60 days. All right, so we have the half-life, we have the value of the half-life is uh, 10. All right, so if you are going to uh, simplify that, that will be one half raised to the power of 60 divided by 10, which is 6. So that is also equal to our exponential form earlier. All right, so we can then rewrite the equation below, which is S sub r is equivalent to A sub O times r, as by using r is equal to 1 half raised to t over ht, and yeah, there we go. So we just substitute the value of r here. All right, so and then afterwards you can try to calculate the half-life if our formula is correct. So sample computation using our new formula, S sub r is equivalent to A sub O times 1 half t all over h sub t, wherein t is the time that has passed by and h sub t is the half-life, which is always constant. Alright, so we can use this table, and we'll try to compute somewhere right here, okay, 60 days, and we will see if it will give us 1.625. All right, so we have SR, so the remaining, this is the original amount, okay, so which is this one, and SR is the remaining amount. All right, so we have 1 half, which is the rate, and 60 over 10, so 60 is the number of days that has passed by, and 10 is the half-life. So we will see that SR, after simplifying 60 over 10, which is 60 divided by 10 is 6, okay, so 1 half raised to 6 is, if you're going to compute that, 1 half raised to the power of 6 is equivalent to 1 half times 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 1 half, okay, so that is 1 all over 32. All right, so this is equivalent to, yes, 1.5625, which gives us our uh, remaining sample, and it gives us a clue, a confirmation that our formula is correct. So that's how we compute the remaining sample using the half-life formula. I hope you have learned how to compute the half-life using our formula and by this video. I hope to see you soon, guys, in our next video. Kindly subscribe to our channel, hit the notification bell, and get updated whenever we post new videos like this. Bye, guys.